Hello, hello, hello. Testing, testing, testing. Hello, hello, hello. Hello, hello, hello. Hello, hello, hello. That's good. Okay. Cool. We're back on. So I left off last time. I actually just, oh, well, I watched it in the morning. My last video at like 1.75 speed or 1.5, whatever it was. And I actually speak at a normal timing when you speed it up. I realize I'm very slow to go through things otherwise. Regardless, I revised what we'd learnt last time. I remember back to the toolbox and how that you start off with a linearly independent set of vectors that's called a um, yeah, just a basis, and then a linearly independent basis, uh, I guess a basis, and then you have the combination of those two forms orthonormal or can form orthonormal um, bases, or an orthonormal basis. And then I remember back to the vector space being um, the whiteboard where you use the tools to draw on the whiteboard the vectors that you want, or to translate to the vectors that are on the board. And then that the whole thing uh, that's everything, right? So that's the separation. Also remember that if you take a linearly independent uh, vector, you can like the very fact that it is what it is. That means that you can form the orthonormal basis. But if it was linearly dependent, it means that you can't, because you end up just scaling the same thing, and so they're never going to be orthogonal to each other. You just end up with like zeroing out the expression. So um, as you go through all the inner products and stuff like that. So I remember this stuff, and I think we left off with actually I'm on the wrong board here. One second. Slow internet. I don't think so. Let me just close this and restart it. Shame, I thought I was prepared. Sorry about this. Just looks like it's deciding to crash. Um, so then we started on this exercise 1.3.1, and I think after going back through it, uh, watching the last episode, um, I started to realize that the rise over run that it was talking about was actually quite important. I was ignoring the fact that if it was I don't know, it was four thirds plus 5/4 or something like that. And of course, if you take those as coordinates, it's y over x. So I know I kind of understand what it was going on about. However, I wasn't sure entirely like how to proceed. So I guess that's what we're going to struggle with today, or I'm going to struggle with, and you're going to watch me struggle. So let me just mark my sheet again. There we have it. Because I'm on a little Surface Book 2. It's a bit slow to be honest, but I have no money to buy something new at the moment. Um, it's also like it's got this ghosting effect where everything on the screen you can still see like many minutes on. So like even if I lock my screen, come back into the lock screen, you can still see what I was what I was looking at before. So I have to be a bit careful of that one. Anyway, it is what it is. I'm not even sure what I'd buy in place of it really, because I need the laptop as well. I wouldn't like to have two different devices. I don't think it'd be a bit of a waste. Anyway, okay, so we're going to start with this exercise 1.3.1, and it says, got a vector. I remember. I'm going to mark the vectors this time because I started to treat it as a normal equation. And I was thinking, hang on, how the bloody hell is this working? And I was like, oh yeah, they're vectors, and I finally put the vector notation back on, and then it kind of made more sense, right? It's also a little bit annoying because the I here always made me think of the complex number, right? So it's a bit tricky that they've done that. Um, anyway, whatever. So I'm just going to write this out. So I got it in my head. What's this one? Wow, I really should learn to memorize things a bit better. Now it says form an orthogonal basis in 2 dimensions, starting with these two. So I think it was saying we can see if something's orthogonal if you take the inner product of the basis and the and some other vector minus the inner product of the first basis multiplied by the basis inner product with the second vector. So we're actually going to take a scaled version away from itself, right? Because one over one that returns a real number, so it'll just be a scalar, um, and yeah, and so these are the same. And I think I had that realization last time, which is then all equal to this this 2 prime thing, which is interesting because it's if I take the normal of it, um, do I get the inverse? I can't remember, or the norm of it. Something like that anyway. So what I have here, let's imagine that this is the basis, right? Um, because here we have this the basis of vectors, and then I'm creating, or sorry, the the orthonormal basis will equal the manipulation of the other two. No, that's not right. So it says let 1 and 2 be a linearly independent basis. They are the linearly independent bases, and then they form an orthonormal basis. Cool. Okay. So in that case, let's take that. Um, our orthonormal basis then would be 1 equals a over the normal of a. And so we then have to start plugging in things. Actually, I remember, let me just go back to the last one because we could just use what I've done there. Oh look, it's on the side here. I've actually got it. Yeah, let's use that instead. But let me just remind myself. This is what I did, right? Yeah, here we go. So I set it to be 1001. Um, well, which is good because they are the linearly independent bases. So you should be able to add them together to get an orthogonal, which is good, right? It's a good one to start with. And then you've got this multiplication of well, multiplying everything out. I think I went wrong here, but this one's correct. So they came out as 0.6, 0.8. So actually, maybe we should just continue from here actually, or maybe I just copy this. One second, let me just copy this out and then. Um, yeah, it's interesting as well because it's actually saying a prime here. So rather than it saying the one that I did, it's got a prime. So let me just do that as well. You can't see what I'm doing, but I like the idea of it, right? I just put up here what the things were. How are you feeling about that purple, eh? It's nice and not nice at the same time. Looks very worky, which I don't quite like. I should probably use a pink next time. Bear with me, nearly there for J is equal to 3, 4. Wonderful. Okay, I think I've got that now. So, and then this will be nearly there. 3, 4 divided by 5. Let me just reposition this, and I think I'm done then. is equal to is equal to 3 over 5 and 4 over 5, which equals 0 0.6, 0 0.8. Alright, okay. So if I go back to my freshie, here we are. It's quite hot today, goodness. Right, there we go. So we got to this point, but it was saying that why don't we think of these as vectors in a plane, 2D plane? So let's do that. I think that's probably a good way to start at least. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then it's going to be 3, 5. No, it's actually, my apologies. So let's say this is 1. So it's 0. Let's make this a bit easier to work with. There we go. Oh wow, what a mess I've made, eh? It's just incredible, isn't it? How stupid I bloody am. Here we go. Let's just do that. Okay, so 0 0.6, 0 0.8. So it's going to be about there. Right, and so if we compare that to the original, which is 3 and 4, so let's smooth this down. I don't know if I'm doing this right yet, but I'm happy to continue. 2, 3, 2, 3, 4. Let's imagine that's 2, 3, 4, 3. Oh, bugger. Fair enough. 4, 3, 2. Here we go. So we want to know what's the rise of this. So it was saying the rise is obviously y over x. So let's do that. It's y divided by x. Y divided by x. Which will give us 4 divided by 3. And then if we negate that, what do we get? So maybe I can do this a bit easier on Desmos. I'm not sure. Just depends. Depends if I know how to bloody use it again. I think I can do. Yeah, here we go. So if I do 0, 0, and then I do no. 0 0.6, 0 0.8, 2, 3, 4, and then we'll do that as a line, right? Can we do that as a line? Maybe here. Lines. Here we go. Here we go. Here we go. Here we go. Oh, bugger. Undo. There we go. Done. And if I do another one, and this will be. Can I make this a different color? This one. Lines. Done. And I'm going to do 4 over 3, and then we negate it, I think. So 0, 0.6 to 0.8, negative 4 over 3. I don't think that's orthonormal, right? So let's see what this is saying again. Um, so it said square root is 5. We got that. So we got our end result. Now to find an orthogonal vector to A, take the negative reciprocal of the slope, considering it's negative 3, 4. So it's negative 3 divided by negative 4. Wait, negative 3 divided by negative 4. Um, the slope of A is 4, 3, so the negative reciprocal is negative 3, 4. Oh yeah, I did this wrong, didn't I? There you go. So 3i plus 4j is let's see. What? Um, so it is. So what? Hang on. I'm confused here. Um, so I have my equations. I've done the calculation here. So 3 times 1 is 3, and then um, 4 times 3i is going to be, yeah, okay, and then it's 4 times 0 is 0, and then 4 times 1 is 4. So because there's 0, I guess it's just, just I don't quite understand actually. Let me try and grab this over and have a little working of this. So I want to know if I go 3 times 1, 0, I equal 3, 0, right? And if I do 4 times 0, 1, I equal 0, 4. And then if you plus them together, I see, if you plus them together, um, this is 3, 0, no, 3 plus 0, 0 plus 4 equals 3, 4. There we are. Okay, cool. So we understand that now. Well, I understand it now. And so then with this, we take the magnitude, which is the the norm, the norm of the norm, which is the square root of the inner product. So we must have taken the inner product at some point. Let's just go back a second. Um, so I think we did do that. Here it is, yeah. So we did a is equal to 25, and we did the square root of 25. Um, but then don't we have to? But then we have to square it, right? So if we go back to our um, no, we don't. No, we don't at all. Well, A prime equals. I just have to warm up because I'm still in the slow gear at the moment. 1 second. Our normal is equal to the square root of 25 because the normal is equal to the square root of the inner product. The inner product was 3 times 3 plus, so that equals 25. Okay, so now we've got our normal, but why are we doing A prime? Oh, it's because of up here, I see. Yeah. Okay. Yes, that's right. Okay, I see. So if I now go back to this, we're we're getting somewhere. And so now this is saying 3, 4. Now to find an orthogonal vector to A, and A was equal to 3, 4. So let's do that first instead. It's going to be 0, 0, 3, 4, and then this one's going to be 0, 0, and then -3, -4. But take the negative reciprocal of the slope. So it's y divided by x. So it's going to be 4, 3. So if I do -4, 3, I've still not got it. It's -4, 3. Using the slope and orthogonal vector to A would be, it says 4, -3. So that's interesting. So I guess I don't know that. The slope of A is so the negative reciprocal. When we say negative reciprocal, what does that actually mean? If I have the A equals 3, 4, and I want to take the negative reciprocal of the slope, I understand that y divided by x equals the slope, and so we'll end up with 4, 3. But why is it that making the y, the new y, the negative, means that's the negative reciprocal? I wonder if, let's also, what is the etymology of the word reciprocal? Here we go. Let's put reciprocal etymology. Cool, okay, we're getting somewhere. Oh my, GPT-4, this is very slow. I think it's because it has loaded in everything above. I guess it's not using something like some memory caching to empty out the top. Anyway, it seems to sped up now. So it says the slope of a line is the ratio of the change in y rise to the change in run, okay, x, and it is often expressed as m equals rise of run. If you have a line with slope m, any line perpendicular to this line will have a slope -1m. The negative reciprocal. The term reciprocal in mathematics refers to the number that, when multiplied by a given number, results in a product of 1. specifically, the reciprocal of A is 1 over A. So the reciprocal is essentially an inversion operation. For example, the reciprocal of 4 is 1 over 4. The reciprocal of 1 over 4 is 4. When we combine the concepts of negative and reciprocal for a slope, we get the negative reciprocal. For your specific example with vector a, 3, 4, the slope of A is m, 4 over 3, and the negative reciprocal of m is negative 3 over 4. This means if you have a line going through the origin with the direction of vector a line that's perpendicular to this line will have a slope of negative 3, 4. And when you say negative 3 over 4, how is that not negative 3, negative 4? Why does the negative only apply to the bottom part of the function, the division function? This is real basic stuff, isn't it? But it's been a while. This is very laggy. I think I might have to let's just try and duplicate this. See if it's a bit faster. It is. Okay, great. Okay, good. So the expression negative 3 is indeed equivalent to negative 3 over 4. However, it's not equivalent to 3. Oh, I meant to say that. Even though mathematically basic expressions, but to clear up any confusion, we say negative reciprocal. We are referring to the concept rather than the placement of the negative sign. You could express the negative reciprocal as negative 3 or 4, or 3 negative 4, and both would be correct in the context of finding the orthogonal direction. The main point is that the value is negative. In mathematics, there's a convention of placing the negative sign in the numerator for clarity, but this is not a strict rule, and the sign can be in the denominator as well. I guess I don't. Okay, fine. That's all fine, and I understand it. Um, but I mean, I understand the end result being important. But now I look at this and I think to myself, which one do I put again? You know. So if I just take this equation, it's m equals um, y over x. I think it was. Is that what it is? Rise over run. Yeah. Um, m equals rise over run. The negative reciprocal is negative reciprocal equals reciprocally. Negative reciprocal is um, m equals negative y over x. And it says when we say negative, we are referring to the concept rather than the placement of the negative sign. You could express the negative reciprocal as I'm sorry, can you explain this in a different way? Why is the negative only done to the numerator? Is it just a rule, a discovery? Oh man, GPT-4 is really slow today. Let's delve into the step by step. What is a reciprocal? The reciprocal of a number is simply 1 divided by that number. So if I do 1 divided by 4 divided by 3, Or maybe if I go 1 divided by 1 over 2 is 1 divided by 0.5 is equals 2. So this is going to equal what? Because if this was 1 divided by 0.5 is 2, if I do negative 1 divided by a half, it's negative 1 divided by 0.5. Does that equal negative 0.2? Negative 1 divided by 0.5 equals negative 2. Okay, I see. Okay, so let's just separate this out a bit. So if we take the 4 over 3, then what's 4 divided by 3? 4 divided by 3 is equal to 1.3. Let's do that. 1.3. 1 divided by 1.3. 0.7. 7. And then now if I do negative 1 divided by 4 divided by 3, I'll get negative 0.08. So something's wrong with my thing there. So let's read this. The reciprocal of a number is simply 1 divided by that number. For instance, the reciprocal of 5 is 1 divided by 5. The reciprocal of 3 over 4 is 1. You say this, but then you go on to show an example of 3 over 4 is 4 over 3. But this isn't obvious to me. One does not naturally follow from the other, in my head at least. Can you help give me intuition? What about the negative reciprocal? When we say negative reciprocal, we're combining two operations. Taking the reciprocal, changing the sign, making it negative if it's positive, or vice versa. So for the number 304, its reciprocal is 4 over 3. Making it negative gives negative 4 over 3. Why is the negative typically on the numerator? It's a matter of convention. Place the negative sign on the numerator is common because it's clear and direct. However, mathematically speaking, both negative 4, 3 and 4 divided by negative 3 are equivalent. They both represent the same value. Why do we care about the negative reciprocal in this context? The slope of a line when multiplied by its negative reciprocal gives negative 1. This property is used to find lines or vectors that are perpendicular to each other in 2D. If two lines are perpendicular, the product of their slopes is negative 1. For example, if one line has a slope of 3, 4, then a line perpendicular to it would have a slope of negative 4, 3. The negative reciprocal. Is it a rule or discovery? It's a foundational property of the geometry of the plane. The idea of perpendicular lines having slopes that are negative reciprocals of each other can be proven using trigonometry and the properties of right angles. It's not just an arbitrary rule but stems from the inherent geometry of Euclidean spaces. Let's break it down. Reciprocal. The term reciprocal has its roots in the idea of returning or flipping. In mathematics, when we talk about the reciprocal of a number, we mean flipping the fraction over. So if you have a whole number like 5, it's like having the fraction 5 over 1. So if you have a whole number like 5, it's like having the fraction 5 divided by 1. Yeah. When we take the reciprocal, we just flip it over. Why do we do this? Consider multiplication. Any number multiplied by its reciprocal gives 1. So 5 times that is 1. That is 1. This makes the reciprocal conceptually useful. It's the number which, when multiplied with the original, gives a product of 1. How does this apply to fractions? For any fraction a over b, where a and b are not 0, for any fraction a over b where a and b are not 0, the reciprocal is b over a. For any fraction a over b where a and b are not 0, the reciprocal is b over a. The reason for this is similar. If you multiply a fraction by its reciprocal, you get 1. Example with let me just do this then. So I need to just get this in my head. If I just move over a bit, actually I'll go before because there's a bit of a prerequisite here. I'll put the little dots again so I don't go off the screen. 1 second. Yeah. Okay. So if I do 6 over 2, the reciprocal is 2 over 6, and that's because if I multiply the two together, 6 over 2 is equal to 3. 2 divided by 6 is equal to, what is that? 0.3 recurring. And so 3 times 0.3 recurring, 3 times 0.3 recurring is obviously 1, is roughly 1. And so so that follows that example, right? So let's now try this with something else. So 4 over 2 equals 2 over 4 because oh, I see. Oh, I see. Because it, like, even if you take, so if you let's just try and manipulate this a bit. So if I were to times this by 4, I times, so it's 4 over 2 equals 2, and then I'll do then I'll go, I want to multiply that out, so it's 4 times 2 equals 2, but it doesn't. I guess I've done something wrong. Let me just start again. If I got 4 times 4 over 2 equals 2. So 4 is 4 times 2. That's not right. So you don't do that. Oh yeah, do. Yeah, that's right. Sorry, I'm an idiot. Yeah. No, you don't. No. 4 divided by 2 is 2. 4 times 2 is 8. It's not 2. If I wanted to do wanted to get 2 on its on its own from the following equation, the 2 on the right side on its own from the following equation, 4 over 2 equals 2 over 4, do I just multiply the left side by 4? I don't think you do. That's the problem, isn't it? Unless you have to do. Let's see. Anyway. Oh wait, that's the problem. Okay, because they're not actually equal in themselves, right? Yeah. That's a good point. So why did they ever put equal? uh, yeah, that's wrong. Sorry. This is just wrong. Okay, but we get the point though. So we get the point. It was actually supposed to be that. So let me rethink about this. And why are we doing this? Um, Fine. Okay, fine. So it is totally fine. I think that's enough to continue on. So let me just move over here. Um, I understand that the premise now. I probably won't forget it at least. So in this case, this will be so 3 over 4 times 4 over 3, and then we'd negate this because these two together equal 1, and we want -1, I guess. So we have to negate it. And when negating it, it just ends up being that this is the one that you need to do. I can't. Everything's crashing today. Microsoft Whiteboard's crashed. 1 second. It does normally wake up at some point. Here we go. Actually, I'm going to do one more thing. If I do 4 over 3 times 3 over 4 equals 1, and I want to get -1, the reciprocal. So if I did 4 divided by 3 times 3 over -4, or 4 divided by 3 times -3 over 4. Let's see which one is correct. In fact, let's just do, to make things life easier. So 4 divided by 2 equals 2, so it's, and then 2 divided by 4, I don't actually, 2 divided by 4, 1.5. Okay, so I meant, sorry, 2 divided by -4, -2, and then 2 divided by -4 equals -2, and then -2 divided by 4 equals 0.5. Negative 2 -2 divided by 4 -0.5. And so clearly then, this one will be 2 times -0.5 is equal to -1. And then 2 times, sorry, I've done this wrong. 2 times negative 2 equals negative 4. 2 times negative 0.5 equals negative 1. And so this is the correct one. So when we go over to here, 4 over 3, we did 4 over 2, 2 over 4. It's the negative 3, 4 over 3. Yes, okay, I understand this now. Okay, good. Sorry about that. Little intermission there. So, in this case, yeah, we've already plotted it, right? So this is the orthogonal thing. Okay, cool. So the next one is, can you generate another orthonormal basis? Form an orthogonal basis. Can you generate another orthonormal basis starting with these two vectors? If so, produce another. Okay, let me just take a snip of this because it's quite nice to see that. And I'm going to delete this thing out. Whoa. Because I don't think I need to see this anymore. I find that quite useful. Good, okay. Let's move on. So it says make it orthonormal, or can you generate another orthonormal basis? So this time we have to to create a normal. We have to divide it by. Oh man, I keep forgetting this stuff. Let me just go back. The orthonormal was. If we wanted to get the normal, we have to square root of the inner product. Yes. Square root of the inner product. Okay, I did know that. So the normal of A is equal to 5. Um, and so then it's going to be um, the first vector of the orthonormal basis will be. I guess you just divide it by itself, right? We've got the normal, but we don't want the normal. We want it to be orthonormal, and so um, it's A prime is equal to um, 0.6, 0.8, and with that, if we did A prime in a product of A prime, we get, so I'm a bit confused at what I would be now. So I guess I would be 3, 4. It'd be uh, A A over, what's it say here? Over the norm squared. And so that equals 25, and this would equal 3 times 3 is 6, plus 4 times 4 is 16, which equals 22 over 25. Um, so the result is that, okay. And then now we have, that can't be right. How did I, so A is 3, 4. 3, 4, and so it's going to equal 3 times 3 plus, oh, it's 9. I'm a fucking idiot. Yeah, equals 1. Okay, that's better. Okay, so now we could create a new, so B prime will equal um, or actually C will equal B. Let's clarify this first one. Okay, so um, I am still on exercise 1.3.1. I have done the following. A equals 3. Oh, wait, am I going high or low? 1 second. I'm going high. That's okay. Okay, just do a little injection. 1 second. Cool. Yeah. So I've done the following. Please assume all letters are vectors with hats. Okay, so it's going to be 3i plus 4j. It asks form an orthogonal basis in 2 dimensions starting with and b equals 2I minus 6j. So I started by assigning I as 1, 0 and j as assigning I equal to that, j equal to 0, 1, because I know these are independent, linearly independent. And then I added the equations together. A equals 3, 4. Um, I then um, I then took the negative reciprocal of this to get an orthogonal vector. That is 4 over 3 is the reciprocal, negative uh, negative 3 over 4 is the negative reciprocal. Then it asks, sorry, does this sound right so far? So you've determined that the vector A is component form is 3, 4. To find an orthogonal vector to A, you're using the concept of the negative reciprocal of the slope, which is a useful trick when working in 2D. If A represents the vector from the origin to the point 3, 4, its slope is 4, 3. The negative reciprocal of this slope is negative 3, 4. To clarify further, if A were a line, any line that has a slope of negative 3, 4 would be perpendicular to A. Let's use this negative reciprocal slope to find a vector orthogonal to A. Let's use this orthogonal to A. One simple way to this is to move one unit in the x direction and then move negative 3, 4 units in the y direction. This gives us the B vector. So is this the next part then? Can you generate another orthonormal basis? No, it's not. This gives us the vector 1, negative, or B equals 1, 3. This vector is orthogonal to A. Now if we want to form an orthogonal basis with A as one of the basis vectors, we can use A and B. However, if we want to use the original B and make it orthogonal to A, then we have to do further processing. But up to now, with your approach, you've found a new vector B that's orthogonal to A, B prime. Okay, so moving on from that, it says, can you generate another orthonormal basis starting with these two vectors? And what did we do? Why is this zoomed out so much? Did I do that? So we were trying to say that because okay, so let's work out B. So that's A, good. And then B, actually none of this is new information here. So I'm just gonna wipe this off. So B is equal to 2 2 6 because of this similar operation up here, right? And so the negative reciprocal of this, let's do that on our calculator. So we've got 0.026, so the negative reciprocal is the reverse of it, and then you take the negative, so that we make sure they multiply to equal 1. So now we've got orthogonal equals 6, negative 2. But we want to take its orthonormal, so it needs to be reduced to 1, right? To do that, we would do um, we would do b equals the square root, but that's the norm. Okay, let's try, because maybe we just multiply by the norm, right? We now divide 2 by its norm to get 2, which will be orthogonal to the first and normalized to unity. Okay, so we just say the normal of this is b divided by b. I calculated, but it says from the two. It says, can you generate another orthogonal basis with basis starting with these two vectors? Oh, but all we've done here is I found out what's orthogonal to A. So it says let's use this negative reciprocal. Like, I feel like I'm missing the point, because here I have simply used A to find the orthogonal vector to A, but I suppose I also want to find something orthogonal to B and A. Given the question notes starting with the two equations, I suppose it was imagining I did something with the previous material um, to find a new basis. The goal of the exercise seems to be to find an orthogonal basis using the Gram-Schmidt process starting with the vectors a and b. In other words, the exercise wants you to derive two vectors from a and b such that both of these new vectors are unit length normalized. They are orthogonal to each other. Let's do this. Start with a. So we've got that. This will be the first vector of our orthonormal basis. Orthogonalize b with respect to a. Project B onto A to find the component of B in the A direction. Projection of B onto A is BA over AA times A. So where have we found that before? Is this on the last one? Given B is equal to 2, negative 6, yeah. Hang on. Oh yes, negative. Yeah, I always do that. Um, it's 2, negative 6, of course. Yeah, orthogonal would be um, negative 6, negative 2, I guess, because you flip it around and then you make the one. So let's just try that. If I did 2, negative 6, then it'll be negative 6, negative 2. Yeah, okay, good. And then, given B is that, then the projection of B is um, what you last said um, seems to be outputting rather than the symbols you meant it to output. Could you read back and improve so I can read it easier? To see if it's going to fix it. Oh, oh, I think it's done it. Nope, almost. I guess 6 negative 24. I don't know. It's really slow though. It's really annoying. Maybe we just have to keep duplicating it or something. Yeah, it's just so much, right? I wonder if they're using some memory cache thing. I don't think they are. Yeah, I don't think they are. So it's anyway, it does this projection, so it's multiplying. So it's doing multiplication of the. It's doing the product of the two divided by the norm, and then multiplying it by, and then it's doing the cross product of 3, 4. Um, you've totally lost me. Yeah, just totally lost by that. man, oh man, is this really slow or what? I don't know what to do about it. I guess maybe I can just delete some of the history above. It's possible, I guess. Yeah, I think that's what I'm going to do. I'm going to try and delete some of the history above. See if I can make this a bit smoother. So let's see if I can do this nice and easy. If I just go and delete a ton of this stuff. Like, I can't. Okay, fine. I just have to do that. Oh, really? Can I not? That's such a shame. Alright, well, it should help though, because it should speed it up. There's less to process on it then. Sorry about this. It's just too slow. I can't use it. We said a lot though. Man, we have done a lot of conversation. Goodness me. Maybe this is already a bit faster now. Maybe. There we go, getting there. Okay, that's probably enough now. Okay. Let's try this again. So it says, apologies for the confusion. Let's break it down step by step in a simple manner. I'll refrain from jumping straight into the math and instead give you an intuitive approach first. Normalize A. To create an orthonormal basis, we start by making our given vector a unit vector, meaning its length or magnitude is 1. For vector A equals 3, 4, its magnitude is 5 from the Pythagoras theorem. To normalize A, you divide each component by 5. 0.6, 0.8. Okay, we've got that. Okay. This A prime is our first vector of the orthonormal basis. Remove A's influence from B. This is essentially like subtracting out the shadow or projection B of B on A. The result will be a vector that's orthogonal to A. The step of projecting B onto A and then subtracting that projection from B gives us a vector that's orthogonal to A. Normalizing the resulting vector from step 2, this ensures the second vector has a magnitude of 1, just like the first one. Now I'll give you a simplified method to calculate the orthogonalized B. Calculate A prime. We already did this above. Find the projection of B onto A. It's B times A divided by A times A. Now let's go back to this. It's B times A. I do not see that anywhere, but I think maybe if I go back one. No, because this was just talking about all the yeah, no. So B times A. So it says find the projection of B onto A. So it's where B and B times A prime is the dot product of B and A. Subtracting this projection from B to get the orthogonal component. B prime is equal to B minus the projection of A onto B. Um, Normalize B to get our second orthonormal basis vector. Now to translate this into numbers, we already found A is that. The projection of A B is that times that divided by that times that. So subtract the above value from B, normalize the vector to get our second basis vector. Do you want to try these steps with the given vectors? I'm here to help you with any calculations or clarifications. I suppose I'm a little unclear how this B times A divided by A divided by A prime times A prime is shown anywhere in the previous parts of the book I'm reading. If we take the Gram-Schmidt chapter, it doesn't actually ever mention this as a means of getting a projection. Is it that I'm supposed to know this already? If so, why would it give me an exercise that's that's requiring skills not produced in this book? See if this is fast as well. Is it faster? Let's see. Let's see. Uh, no, it's not. Interesting. So they got some just new bug, I guess. The Gram-Schmidt process, which you seem to be referring to, is a systematic way to orthogonize a set of vectors and then normalize them to produce a orthonormal set. The process inherently uses the concept of projecting one vector onto another, though it may not always be presented with the exact formula for projection in every source. The basic idea behind the Gram-Schmidt process is start with your first vector, normalize it. For the next vector, subtract off the component in the direction of the first. This is the projection, then normalize the result. For the third vector, subtract off the components in the directions of the first two vectors, then normalize the result, and so on. Each subtraction is essentially removing the projection of the vector onto the one that came before it. In mathematical terms, if U is a normalized vector from the set you've already processed and V is the next vector you're working on, then the component of V in the direction of U is given by. In the Gram-Schmidt process, we systematically subtract off these projections to make our vectors orthogonal to all the previous ones. So when you say the book hasn't mentioned the formula of projection, it's likely that the book introduced the concepts in the context of the Gram-Schmidt process without explicitly stating the formula. It's a common teaching approach to introduce the concept and its application before formalizing it with formulas. If your book didn't introduce this and jump right into the exercise, I understand how that could be confusing, but now that you're aware of the projection and how it plays with, you're equipped to tackle such exercises. Not so sure. Okay, well, what's this? What's this symbol? I think it's the cross product, isn't it? Um, is the x you've used the cross product? If so, how does one calculate the cross product? No, the symbol x I've used denotes regular multiplication, not the cross product. In the context of the projection formula, it's just scalar multiplication of a vector. However, since you brought up the let's briefly discuss it. The cross product is a binary operation on two vectors in three-dimensional space. It produces a third vector that's orthogonal perpendicular to both. It produces a third vector that's orthogonal, perpendicular to both of the input vectors. The magnitude of the resulting vector is equal to the area of the parallelogram spanned by the two input vectors. The cross product is denoted with the cross and is defined as okay. Oh, I feel like I just completely lost the plot here. It's so upsetting. So I thought I was following on, right? So anyway, it says b times a divided by a times a, and that's the projection of a onto b. And so it's going to be it's 2 times 2 negative 6 times 0.6 0.8 divided by 0.6 0.8 times 0.6 0.8, which equals so 2 times 0.6 is 1.2, negative 6 times 0.8, I don't know, negative 4.8 divided by 0.6 times, oh, so 0.6 times 0.6 is probably like that. 0.6 times 2 is 1.2, yeah. So 0.6 times 0.6 is 0. Wait, 0.6 times 0.6, 0.36, and then 0.8 times 0.8, 0.64. 2 times 0.6 is 1.2. Negative 6 times 0.8. Negative 6 times 0.8. Negative 4.8. And then it says times by a. Which equals 1.2 times. Well, let's divide. Can you? I don't think you can divide them, can you? We'll try it. Um, 1.2 divided by 0.36 negative 4.8 times negative 4.8 divided by 0.64 negative 7.5. It's just again 1.2 divided by 0.36. Yep. And then 6, 0.8. So it's this 1.2 divided by 0.36 times 0.6 is 2, and then 0.6 negative 7.5 times 0.8 equals negative 6. Oh, fuck me. Okay, fair enough. That wasn't obvious to me. So we think we probably have got that about right. So that's the projection. Now subtract the values from B. So then you got, yeah, equals 0. Negative 6 take away negative 6. I think that's right. Negative 6 take away negative 6. Negative 6 take away negative 6. 0, yeah. And that means that's orthogonal. So so normalize the result to get our second basis vector. Subtract the above from B, we'll end up with 0. If I do B times A divided by A times A equals 2 negative 6 times 0.6 0.8 divided by 0.6 0.8 times 0.6 0.8 all times 0.6 0.8 equals 1.2 negative 4.8 divided by 0.3333 0.64 multiplied by 0.6 0.6, 0.8 equals, oh, sorry, 0.3 recurring? No, 0.36 is equal to 3.3 recurring negative 7.5 times 0.6, 0.8 equals 2, negative 6. Now, if I subtract that from B, 2, negative 6, take away 2, negative 6 equals 0. 2 minus 2 is 0. Negative 6 minus negative 6 is 0. I can't normalize this, can I? You're right, let's retrace the steps using the ground shift, which is used to orthogonalize a set of vectors. The idea is to project one vector onto another and then subtract the projection. Start with vector A, which is 3, 4. Normalize it to get A. A prime is that? Yeah, we got that. Yep. Next, to orthogonalize B with respect to A prime, compute the projection of B onto A prime. 2, negative 6, 0.6, 0.8, 0.6, 0.8, 0.6, negative 4, 1. Really? Negative 4, 1. So I guess I did this wrong. So 0.6 times 0.6 is 0.36. 0.8 times 0.8 is 0.64. I did do that right. 0.64. Yeah, I did do that right. 2 times 0.6. Subtract the projection. We will get that, but now B. No, I made a mistake in my previous explanation, so I apologize for the confusion. You are understanding the process correct. Subtract the projection from B to get the vector orthogonal to A. B. How is 2, negative 6, 0.6, 0.8 divided by equal to negative 4 over 1? Oh, it's plus. Okay, so I didn't realize that was the. I thought it was fucking multiplication. So I didn't. I didn't realize. Ah, I just didn't realize. So here. Oh, that's so annoying. I see now. I see. Okay, okay, we got it. We got it. We got it. Okay. So this is actually the dot product, of course. So it's gonna be two times 0.6. In fact, if I just go back one, it's actually plus Um, it's it's plus, and is that what it said here? 2 times 0.6 plus 0.8. So yeah, plus equals. Aha! I see. So it's, so 1 point. Uh, wait, what has it got here? So 0.6. Dot product of A with itself. 0.6. Yep. 2 times 0.6 is 1.2 minus 4.8. Um, I see. I see. Yeah. And this would be, so, was that 1.64 or 0.64? I see. 64, and that would be plus. So that would be 1.2 take away 4.8 equals negative 3.6. Yeah. So it's equal to negative 3.6 over. Now B should be orthogonal to A. Divided by, let's just do this, 0.36 plus 0.64 equals 1. So it's equal to that, negative 3.6, and then you multiply by 0.6, 0.8. Let's see. So 3.6 divided by 1 is going to be, yeah, negative 3.6, and that will be, I mean, possibly that. Okay, fine, yeah. And then to get B, you subtract the projection from B. Now B should be orthogonal to A. So let's take these numbers and see. So if I do, so A is 3 and 4, and so I don't think this is going to be right. 4.16 negative 3.12. Well, fuck me, it is. Um, I guess it's not actually, but um, they're awfully close. So maybe someone's gone a bit wrong here because we are probably not taking into account the. Yeah, so let me just put this into Python or something. 1 second. Python online. Agreed. Yep. So if I do um, A equals 2 times 0.6, B equals negative 6 times 0.8, A times A. Why is it minus though? Minus 6. A plus B equals C. And then it's, see, we'll go numerator, denominator A equals 0.6 times 0.6 dB equals 0.6 times 0.8, sorry, times 0.8. The denominator C is equal to dA times dA plus dB, and then you've got output equals dnc divided by dc times 0.6 OB equals NC divided by DC times 0.8. Let's try that. Let's print out OA. I think I could do that actually. I think so. Maybe something like that. Is it like that? Don't know. OB. Let's see what happens. Run. Negative 216, negative 28. And then we'll go uh, original equals original or A equals 2 or B equals negative 6. New equals or A OA minus or A. New B equals OB minus or B. And then we'll print that. Okay, so this is 312. Oh no, I don't know what that means. Cool. 3119, 3119, yeah. So they're not orthogonal, are they? These are not orthogonal. But 4.16 negative 3.12 is not orthogonal, not exactly orthogonal to um, negative 6. Not now B should be orthogonal to A, sorry. 0.8. Oh, hang on. A prime it's saying here. So A prime was 0.6, 0.8. Ah, but there's surely the orthogonal. Let's try another one here. Let's go. Oh, I'm just getting so confused. If I go 0, 0, and I go 0.8, negative 0.6, yeah, they're not going to be precisely the same, right? But they are. They're exactly the same. Fair enough. All right. Wow, that's amazing. That's amazing. I guess that's not okay. Fine. So you take the dot product. Okay, fair enough. Who knew? Um, that's immense, and actually kind of helpful to draw these things right on the table. It's just been completely scaled. That's all. Um, and if I wanted to normalize these, I just have to yeah, if I do 0.6, 0.8, and then I would go negative 312. Oh, well, yeah, that's not going to work, is it? Of course. But I guess you'll get, so this will be 1, 1, and that will be 1, negative 1. Ah, yes, of course. Normalized. Okay, cool. Uh, yeah. All right. Huh. Interesting. That was a surprise. Okay, good. Oh, we've learnt something there. Um, awesome. Let me just check my blood sugars. And so, let's see the next. Can you generate another orthonormal basis starting with these two vectors? Uh, if so, produce another. And so then you would just negate the second one, right? So maybe we should do that to finish this off. Whew, that was a lot. That was a lot to take on there. Um, let me just resize this a bit. Yeah, like that. And do that, and then do 100%. Bear with me. Okay, where are we? Here we are. And here we are up here. So I want this down here. I think I'm gonna have to take a quick break. I think I would like to come back to this because I'd like to get onto the second page now. But I think we made some progress here. It'll be good to just take a moment's break because then I'll absolutely know and have some revision on it that I've done it right. So I'll be right back and I'll do a point one of this. Thanks, guys.